So we kind of stopped yesterday at a point where we looked at the first version of our LNA, and clearly it didn't work for us. It didn't work for us because it gave everything except for noise figure, low noise figure, which is really the most important spec for an LNA. Okay, so it is just not going to be good enough. So let us go back. So as I pointed out, the noise produced, of course, by any physical resistance or any matched Thevenin resistance is going to be the noise produced by a physical resistance of that value, right? So if you, whether you add a resistance in parallel like this, whether you add a resistance in parallel like this, or use some physical resistance which will produce thermal noise to match up to 50 ohms, it does not matter, you're going to produce the same amount of noise. Okay? So we need to come up with new ideas as to how to match without a resistor. So I'm going to solicit ideas from you folks. Let's look at the MOSFET itself. Impedances at various nodes. The problem comes because you wanted a high gain amplifier, you chose the common source amplifier, which happens to have a capacitive input, right? Okay, so choose a different type of amplifier which does not have a capacitive input. Maybe that might perform better, right? That's your hope. So that's a good place to start. So what other amplifier types of amplifiers do you folks know? Common source, common gate, and common drain. These are the most common ones, right? Okay. Look at the common drain. It does not have any gain. It has a voltage gain of 1. That is not good enough for us. Okay. Fine. So that's out of the picture. The only other possibility is the common gate amplifier. Okay. The good thing about the common gate amplifier is that the input impedance is very low. It is not capacitive. It's very low. It's resistive. Therefore, you have a chance to make it 50 ohms by design. So that's what we'll look at today. Before we go there, one quick point about the MOSFET, noise. So we have been assuming that the noise of a MOSFET is 8 kT by 3 times GM1 delta F, but in reality it is better expressed as something like this. Okay, so in general the noise of a MOSFET can be in saturation can be described as 4 kT times some parameter gamma times GM delta F. This is the noise. So noise pass spectral density is 4 kT gamma GM. Now what is this gamma? Gamma is often called the excess noise factor. Okay, normally this is 2/3. It is 2/3 for long channel MOSFET at low frequencies. Okay, your analog IC design, this gamma will never come up. Okay, it's 2/3. So you just write it as 8 kT by 3 times GM. Okay, unfortunately, in many RF circuits, you use minimum lengths which are extremely small, 65 nanometers, 130 nanometers, and so on, right? Maybe even smaller. Okay, when the length is so small, measurements seem to show, it's not a closed case, but measurements seem to show that there is excess noise at higher frequencies. When you have short channel devices operating at very high frequencies, hundreds of megahertz, if not gigahertz to tens of gigahertz range, the noise is pass spectral density, first of all, may not be flat. Okay. Number 2, the gamma is not 2/3, it's higher. There is some excess noise. Okay. So I'll just say gamma is greater than 2/3. For example, it could be 1, 2, 3, etc. Like numbers like this. So you expected 8 kT by 3 GM, but you may be seeing maybe 2 times, 3 times, 4 times as much noise. Okay, and when you are calculating the noise figure, you have to take this into account. So going forward in this course, we will use this expression for the drain thermal noise pass spectral density and not 8 kT by 3 GM. Make sense? Okay. How will you really design a circuit? Yes, you had a question? Absolutely. So first question, suppose you design a common gate amplifier for an input resistance of 50 ohms. Does it give lower noise than a physical resistance, or higher noise than a physical resistance? You will never know till you calculate the noise figure and check. So that's why we are taking the detour. Okay. Any other questions? Because the common gate amplifier offers little bit of, the noise is different from a physical resistor, right? So let's just quickly calculate that. It only takes a few minutes. How do you figure out what gamma is? Hopefully, if the process is being used for RF design, the foundry would have characterized high frequency noise. So what you do, you go in, simulate, extract out gamma, and then run your design for that. You will know what noise figure you expect. Okay? If not, you're fresh out of luck. Common gate LNA. So Rn is 1 over GM. Okay. So first let's draw the full common gate amplifier circuit. So clearly this is, let's take a transistor M1. The input is going to be applied at the source of the transistor. So can you just connect RS and DS? You have to capacitively couple it, of course, as always. How do you bias the transistor? You can add a current source if you want. Some current I0. What do you do next? What do you connect the gate to? Some appropriate bias voltage. I'll call this some VB1. The bias voltage is chosen such that the current source has enough headroom. Right? VB1 is equal to VGS1 plus the voltage across the current source. Okay? What do you do on the upper side? You put the output, but very often, because you want more isolation between input and output, okay, you may add a cascode transistor, even for the common gate. To improve isolation between input and output even further. Okay. What do you do at the drain? You can put a resistance, but we know that you can do even better by putting a tank circuit. Remember that this resistance is RP. You never put a physical resistance unless absolutely required. That resistance is the parallel resistance of the LC tank. I call this LD and CD. How do you choose VB2? Yes. I said RP is not a physical, I just finished saying that. Yesterday also RP was not a physical resistance. Yes, correct. So, Where does RP come from? Huh? What? What do you mean by LMC? What is that non-ideality? Huh? Okay. That metal has a finite series resistance. The capacitance has leads that may have resistance. You may have leakage through the dielectric, etc. Those are all physical resistances. Many of those resistances are physical resistances. They will produce noise. Okay. If you have a series resistance with LD, it will produce noise. When you convert that series equivalent to a parallel equivalent, it will produce noise equivalent to that parallel resistance RP. Any other questions? How do you choose VB2? VB2 should be high enough such that M1 is in the saturation region, well in the saturation region, right? VB2 is equal to VDS of M1 plus the voltage across the current source, right? So you need to make sure the source of M2 or the drain of M1 is much higher than 1 VT below VB1. That's what I'm saying. You need to have enough headroom such that that is in saturation. But if you keep making VB2 higher and higher, okay, M2 itself can go into the triode region. But the good thing is the drain of M2 is already connected at VDD. That is the highest voltage possible. Okay, so worst case, even if you connect VB2 to VDD, you will have at least 1 VT swing at the output, which is actually quite high for an LNA. Okay, one threshold voltage is a few hundred millivolts. Okay, typically the input coming into the LNA can be as small as about minus 100 dBm power. Okay, so you're talking about probably microvolts, tens of microvolts. Okay, the typical gain of a single stage of the LNA will be about 20 dB. It's about a gain of 10. So the signal swing at the input of the LNA can range from microvolts to maybe millivolts. Okay, so the output can swing anywhere from maybe tens, hundreds of microvolts to maybe several tens of millivolts. Okay, fine. Of course, that CD may consist of some load capacitance plus the drain bulk of M2 plus drain gate of M2 plus some fixed capacitance also may be added by you. So this is your common gate LNA. So first question. In the case of the previous LNA that we looked at, which was one version of the common source LNA, right? What was the input impedance of the transistor? CGS. Very high, but at high frequency is CGS. Okay. What is the input impedance of this get? On the GM in parallel with 1 over SCGS1. Please remember this. You don't have a free just 1 over GM by itself. You also have a capacitance. This capacitance is almost equal to the original capacitance earlier that you had. So you most probably need an inductor. In a majority of cases, you will need an inductor to resonate this out. Okay? You may do something like this. Okay, you can get rid of the current source and use an inductor to bias it. That is also acceptable. This is version 1. Version 2 can look like this. Just 1 minute, folks. You can do this. Okay. Normally you don't want to send, you will still need the capacitance, infinite capacitance, because you cannot send any DC current through DS. Okay. You may think that anyway the output is biased at ground, why do you need the infinite capacitance? Okay, you don't know what is coming from the other side. It may be a filter, it may be the antenna, it may be something else. You do not want to send DC current, your own bias current, into the previous block. So you will still need the infinite capacitor. Any questions? You might use this, so that this L will resonate out with the capacitance at the input. In either case, you will choose L such that it resonates with CGS1. You will also choose this. Choose the output to resonate exactly at your frequency of interest. Okay? So, first question, what are the other specs? Input resistance of the LNA should be 50 ohms. The minute you resonate CGS out, okay, set GM1 to be equal to 20 millisiemens. Yes. Yes. I did not say the which inductor? Just L. We are not using it as a current source. You are not using it as a current source. So I'll write this down here. VB1, VGS1 plus minimum current required for the current source. In this case, VB1 is only equal to VGS1. You do not use it as a current source. You are using it to resonate out the capacitance. Okay? Any other questions? I didn't understand. If you have some difference between the input resonance and the output resonance, what will happen is that the peak gain will reduce, but the circuit will become more broadband. Right? Imagine you have two narrowband circuits cascaded with each other. They are a circuit like this, two circuits like this. In this case, because the input and output are completely isolated through the common gate and the cascade, okay, the two resonances will hopefully be completely independent. If that is the case, the two resonances will just get multiplied with each other when you calculate the overall transfer function. Okay, so the overall may look something like this. Right? If you push them apart even more, you'll start getting stuff like this. Yes? Got a question? No. Her question was what happens if the two resonances are not the same? What you are saying is correct. As he is pointing out, if you have two resonances which are right on top of each other, the bandwidth will shrink. Okay? Bandwidth will indeed shrink. But what she's talking about what happens when the two resonances are not the same. Then the bandwidth will indeed expand. Okay? This is a very common way of making circuits a little bit more broadband than what you originally could do by keeping the resonances slightly off. Okay? I hope you got what she's trying to say. Any other questions? Yeah, if what happens? Yes. Why would the peak come down? Yes, that is, well, okay. So I have basically shown what happens, but yeah, if you could put both of these together, the two gains will line up and you will get higher gain if you had both concentric balls. In fact, that's what I said right at the beginning. I have not shown that here. That's correct. The gain will slightly reduce, circuit will become slightly more broadband. That's what I started off saying. Because if the two resonances were lined up on top of each other, the two gains will add up, you will get a higher peak and a narrower response. If you place them apart, you will get a lower gain, but you will get a broadband response. Okay? Okay. So, first step, so we have managed to get a circuit going. Zn is purely real and it is 1 over Gm. Okay? So you have to set Gm1 to 20 millisiemens. Now, the most common thing to do is to set M1 and M2 identical, because it's after all a cascade. You don't have to do it, but it's very common. Why would you do something different? So what is the gain of the circuit? So remember, in a perfectly matched condition, the source voltage of M1 is exactly Vs by 2, right? So the input current is what? The input impedance is 1 over Gm1. So the input current is Gm1 times Vs by 2. Most of this current will flow upwards through M2 to the output, right? Because you have an impedance 1 over Gm looking hopefully very small. The impedance looking downwards is RDS. So hopefully most of this current will go to the output. So what is the output voltage? It is basically this current times Rp. So one of the reasons why you would make M1 and M2 identical is so that most of the current goes upwards. If you start making M1 smaller than M2, for example, the impedance looking upwards becomes larger and larger. Okay, already the GM RDS of this device may be quite small, maybe 10 or 15. Okay, at these frequencies and with these sizes. You don't want to compromise, so you probably make that the same size. So that 10, if GM RDS is 10, if you make them equal sizes, probably 10 11ths of the current flows upwards and 1 11th of the current flows downwards. Okay. What is the gain of the previous circuit? Minus GMRP by 2. Right, the magnitude of the gain was the same. Okay. Remember that the common gate gives you non-inverting gain. The common source gave you inverting gain. That's not a big problem. A 180 degree phase shift is no problem at all. As long as it is constant 180 degree phase shift across the band, you don't have any problem at all. Okay. Okay, so gain Zn. Third thing was noise figure. Right, let's quickly calculate the noise figure. So there are two versions of the circuit, one with the current source, one without the current source. We'll do the case without the current source, but you have to remember that the circuit with the current source will probably have more noise because the current source itself will add noise. Okay, so normally you would use version 2 if you want to push down the noise even further. We don't need this capacitance, we are doing only for the signal. Okay. INRS squared. Four sources of noise. We are trying to calculate the short circuit noise. So, first thing is that L itself may have a parallel resistance. We will ignore that for now, but please remember that will cause your noise to change a little bit. Okay. What will happen if L has some parallel resistance? Let us say it has some resistance R. What will happen? Of course, that will produce noise, number one. But more importantly, it will change your input impedance. Okay? So your GM may no longer be 20 millisiemen. Okay? So that resistance needs to be larger, so GM may need to be slightly smaller than what you expected. Be prepared for effects like this. Okay? But for now, we'll ignore this R. If GM becomes slightly less, IN1 will, change. Please remember that. So your noise figure may shift slightly. Okay. Can you write it down based on inspection? INRS squared. What happens to this noise? Half of it will flow through the transistor M1. It will flow through transistor M2 and flow through the short circuit. Okay? So what is this value corresponding to that? Good. Okay? INRS squared divided by 4. IN1 squared remember this trick you learned in analog IC design, you'll have to use that here. Because you have a finite resistance on the source and the load. On the load side, you actually have a short circuit, so you may get away without doing it. Okay? So maybe I'll show one of these using a different color. What is the total short circuit noise? This gives you a current IN1. This current, what happens to this red color current source? you have RS looking downwards, only half of it flows back into the transistor. Okay? This is okay? So you basically split that current source IN1 squared into two correlated current sources. The black one, IN1, pulls out current from the short circuit and all of it will flow through the short circuit. The red one has the option of splitting between RS and the input impedance of M1, which is also equal to RS. So only half of it will flow up, half of it will flow back through RS. So that half current will flow through the short circuit. So you have IN1 by 2 resultant current through the short circuit. Noise from N2, yes. Because oh, thank you. It is not, but there is a 1 over GM and then a short circuit. I should not have shown it like this. It is almost a short circuit. Okay, what about IN2? Most of it will end up circulating inside the device itself, right? So IN2 does not exist. What about INRP? All of it will flow through the short circuit. Total noise over noise at the output due to the short circuit alone. I mean, due to the source resistance alone. To be exact, this is actually noise factor, not the noise figure. So nowadays both are used interchangeably. Okay. Noise figure is in dB, noise factor is the linear term. 1 plus 4 kT gamma GM by 4 plus what is the third term? Huh? Oh, sorry. 4 RS by RP, correct. Thank you. What is the third term? Huh? Gamma GM RS. Okay. This is GM1 RS. What is GM1 RS? 1. Because you set 1 over GM1 to be equal to RS. Excuse me. Okay. So the noise factor, the noise figure of a common gate LNA is 1 plus gamma plus 4 RS by RP. Okay. So first question, this is the best one, even without a current source. If you had a current source, you will have some extra contribution from the current source also. So if RP was very large. Alright? So you can imagine why each of these terms is coming up. Of course, the one term comes because you have contribution from RS also to the total noise figure. That's okay. One always comes in. Why does the gamma term come in? When you had a physical resistance, the additional noise due to input matching was just 1, because the noise due to it was 4 kT RS prime. Here it is 4 kT gamma GM1. GM1 is 1 over RS. Right? So that gamma term is the additional noise from the transistor compared to using a resistance. Does this make sense to everybody? If you had used a physical resistance, you will just have the same noise as your source resistance. But now the transistor is producing gamma times that noise. Okay? The resistance would have produced a current noise equal to 4 kT by RS. This one is producing 4 kT GM into gamma. So you are now getting that, because that is adding right at the input. Okay? So you will get that gamma term right there. The next one is telling you have a 4 RS by RP. So the gain of the circuit, what is the gain of the common gate amplifier? What is the gain of this circuit? GM1 RP by 2. Okay? RP by 2 RS. Okay? The gain of the circuit. So that third term is related to the gain of the common gate LNA. Why is that happening? If you had a larger gain, the signal will be much larger at the output compared to the noise added by RP. So as the gain keeps getting larger and larger, the contribution from RP should keep getting smaller and smaller. Does this make sense to everybody? So this also makes sense. Okay? So, okay, so the best you can do is when RP is infinity. You get as much gain as possible. Yes? You had a question? I thought somebody raised their hand. Okay. What about, yes? Yes, what about this? Not a parallel resistance, it will have a noise, drain terminal noise. What is the current source? This is a current source. Right? What else is a current source? If not just a transistor with long length and a bias voltage. Okay? You will of course design it such that it has as low a VD-sat as possible. The minute for a given current, if you design it for very low VD-sat, okay, it means that W over L is very low, okay, W over L is very high. Automatically that means that GM will be high, noise will be higher. You probably don't want to do that. Okay, if you go the other way, try to minimize its noise, its VD-sat will keep getting larger and larger. Okay, which means the effective IIP3 of your LNA will keep getting smaller and smaller. Okay, there will be some linearity constraint. Any questions on the common gate LNA noise figure? Okay, so let's assume that RP is infinity. You have as much gain as possible, noiseless. Gamma is 2/3. Okay, what is the noise factor? What is the noise factor? 1.67. What is this in dB? Better than 3 dB for sure. 2 is 3 dB. Can you please calculate what 1.67 gives you? .2 dB. So, if you had no noise from RP, okay, and if you had a long channel MOSFET, so excess noise factor, this gamma factor was 2/3 the same as for a long channel MOSFET. Okay, this would be 2.2 dB. If gamma happened to be large, like if gamma was 2 for example, okay, you're done for. Okay, it's much worse even than. So what this is telling you, if the transistor gamma was such that the transistor was noisier than a resistor, right, then you are done for. So the common gate is still not the LNA that we are looking for. It still has certain advantages. Okay, people do use it occasionally, but it's still not good enough. Even in the most ideal case, it gives you only 2.2. I want less than 2 dB. I want 1.5 dB or something like that. Okay? How do you do this? We'll get started today and then complete tomorrow's in next class. So, ideas. What are the other ways in which you can generate? So, one way is to, so let's go back to the original structure where we had a 50 ohm resistor. The problem is that the 50 ohm resistor adds as much noise as the your source resistance. That's why the noise figure is at least 3 dB. Suppose I found out a way to use the resistance larger than 50 ohms, okay, but still get an input of 50 ohms. The current noise from that resistance added at the input will be smaller and I might get a better noise figure. Right? That is indeed possible. So, how would you use a resistance like that? You might have to use feedback. Use a resistance and feedback. Okay. So, normally, to apply feedback, you have to be very careful. Okay. Now, if you build an LNA with feedback, by default, you are trying to say that the circuit is not unilateral. Just remember that. Originally, you wanted it to be unilateral. Now you are saying, hey, it's okay if it is not unilateral. That is something you have to remember. Right? Because the minute you apply feedback, you have to worry about stability. We were trying to get away from worrying about stability by making the circuit unilateral, by making the Y12, whatever, the 1-2 parameter as small as possible, so that the LNA will be unconditionally stable. But the minute you apply feedback, it's no longer stable. Okay? Now, in what ways can you apply feedback? You can apply resistive feedback. Okay? I can choose RF carefully such that the input impedance. Remember, in analog circuits we chose RX. So, in analog circuits, right? This overall input impedance is already only 1 over GM. Okay. When you are driving it with an ideal source, ideal voltage source, it doesn't matter. Okay. If you had a source with 50 ohms, you can now show that, maybe I'll call it RF, why RX? You can now show that the input impedance will be functions of both, of course, the GM of the transistor as well as RF. So one of the homeworks for today is to find out, so for example, if I had a circuit like this, maybe like this. Okay, what is the input impedance of this circuit? Okay, what is the input impedance of this circuit? What is it actually? RF. If I use an ideal tank circuit, what is the input current? None of the input current can flow through the tank. It has to flow through the transistor. Why is it CGS? At low frequencies, at high frequencies. What is the impedance at low frequencies? Okay, so the current can, at high frequencies, current can flow through both CGS and the transistor. At low frequencies, current will not flow through CGS, only through the transistor. So at low frequencies, what is the input resistance? 1 by Gm. If you have an ideal tank circuit, it's 1 over Gm. Right? So, the case with an ideal tank circuit, it will just be 1 over Gm. Okay, in parallel with CGS, the impedance. Yes? Yes, absolutely. Because I can always decide to resonate the tank at lower frequencies. I can always choose to resonate the tank at higher frequencies. As always, in all of these circuits, we are analyzing the amplifier only for the frequency of interest. Okay? Yeah, you set F0 to the desired frequency. It could be low or high, and then you would figure out what happens. Okay? So now with RP, I want you to calculate. The homework for this today is, what is the input impedance? Okay? Assume that you can resonate out CGS using some inductor. Let's make this a truly narrow band LNA to make things easier for you folks. Okay, L resonates with CGS, LD resonates with CD at your frequency of interest, and I want to find out input impedance. Okay. Okay, sounds good. Let's stop here.